Okay, I think we're ready to get this show on the road. We have an energizing session this afternoon called Small Utility Innovations. I'm AlexAnna Salmon. I'm the Tribal Administrator for Igiugig Village Council. We're located in Southwest Alaska, probably one of the smallest utilities in the state. We have three panelists here today, and the first presenter is Bill Stamm. He's the Manager of Engineering for Alaska Village Electric Cooperative. He grew up in Connecticut and graduated from the University of Connecticut with a Bachelor of Science in Civil Engineering. He moved to Alaska in 1993 and worked for AVEC, installing, maintaining, and designing power generation and distribution systems. In the last 10 years, with various funding agencies, Bill has assisted AVEC in building 12 new power plants, installed 34 wind turbines, and made renovations to tank farms and distribution systems. His presentation today is titled Modernizing the Powerhouse. So if your community is looking to upgrade, please listen closely for lessons learned. Help me in welcoming Bill Stamm.
If anybody's seen Dave Lockhart's presentation just on the last session, I've got my work cut out for me because he covered a lot of the same material that I'm going to cover. He took an hour and a half, and I've got 20 minutes. But I'm going to delve a little bit into more of the details of some of the items that we have in our power plants, how we're actually running our variable speed drives, what we're doing to increase heat recovery, that sort of thing. There we go. Just a brief background on AVEC. We supply power to 56 rural communities. We've got 49 power plants. We've got 34 wind turbines right now that are feeding power to 14 different communities. And some of the stats about the fuel that we burn. One of the big things for AVEC is that we just recently acquired the Bethel utility. So up until this time, you know, we generated about 78 million kilowatt hours a year, and with Bethel added to our system, now we're going to increase by about another 40 million kilowatt hours in a year. In any design, there's always different competing needs. Obviously, you want functionality, reliability. Cost is a big component. And one thing that all my maintenance guys keep driving is maintainability. We can go out there and build a power plant, and we think it's all really nice. But then when the mechanic has to come in and swap out a head, and he sees he's got, you know, 6 inches to the wall and nothing overhead to lift up the engine, he gets a little upset. So you have to take in a full realm of possibilities of what could happen to that unit. A couple of the topics that I'd like to cover, and you'll have to give me a little bit of leeway because I am a civil engineer. I went all the way back to outside the plant. Before I got into the plant, I want to talk a little bit about siting issues and that sort of thing. As David had mentioned in his presentation, one of the big things on diesel generators is to get any parasitic loads off the engine, so you pull off the engine-driven fans and that sort of thing. Put in remote radiators with variable speed drives. Along hand in hand with that is having a combined cooling system, which goes hand in hand with developing heat recovery systems. We've also now moved into the realm of automated switchgear, so we can control these engines, load share, parallel, match loads more efficiently. We've got fuel systems. David touched on the importance of oil blending in his speech. I'm going to talk a little bit about the way we're blending oil in our power plants and the benefits there. Another innovation that we're doing in a lot of our power plants now, we have single battery systems that power all of our power plants, start all of our engines, maintain 24 volts for control systems, that sort of thing. And we've seen over the years that with the needs of these electronic engines, more finicky PLCs and that sort of stuff, we really have to maintain a good power system. So what we've been doing is integrating ultracapacitors into our battery systems to support those loads. If you have big dynamic moves, like if you're cranking an engine or something, a lot of times that depresses the voltage. If you end up coming into a lot of money and you get to start from scratch, there's a lot of things you want to consider when you're designing a power plant. Obviously, you got to have access. You have to get fuel to the plant. This is a picture of NOATAC. You might think that the best place to have your plant is where we have our, sorry, wrong button, is where we have our plant right on the river. But barges can't actually get up the NOATAC River anymore. So we get fuel flown in. So you have to build a fuel line from wherever the fuel supply is. Obviously, if you can recover heat, that is going to be one of the greatest benefits for your plant. AVEC is a little bit different than the state because we're a power company and we really don't have circulating heat systems and that sort of thing, so we really have to rely on partners in order to make a heat system viable. Soil condition is a big factor in your power plant design, whether you've got available fill and those sorts of things. Permafrost is a big challenge for any sort of heavy construction out in the bush. And then power distribution, property ownership, and future development. This is an older picture of NOATAC. A lot of times we like to partner or position our power plants where there's going to be a heat load. The school for NOATAC used to be right here. Now the school is up over here, and they're usually a pretty good off-taker for heat. So knowing what the village is going to do and where they're growing is also a big component. And of course, there's weather conditions. We get high water periodically, and every year the water freezes and blows around. This is one of our power plants in Chivac. I just wanted to kind of run through some of the design components in this plant. It's up on piles. It's a permafrost area. It is close to a river, so it's above floodplain. It also gets things up out of a snowdrift configuration. We've got 3 generation modules and a control module. What you can't see here is there's a corridor across the front of that, a covered corridor, and then there's some storage modules on the other side. One of the components that you have to worry about in snowdrift villages is how you do your intake air. You really want to slow the air down so you don't get a bunch of drifting snow inside your power plant. We've also got our plant transformers up on a deck so that they're accessible year-round in case you have to go in there and check fusing or pull elbows. One of the deficiencies of this setup that we've been doing for many years is the thermal efficiency. Obviously, you've got a lot of surface area in these individual modules, and if your main goal is to retain heat and send it to somewhere else, you don't want to use so much heat in the power plant. One of the benefits of this structure is if this module caught fire and burned to the ground, we'd probably still be able to maintain power with the other units. So we call it a snowdrift configuration. This is a picture in Savunga, a very similar plant. Again, we've got storage modules, generation modules, control module, and storage modules. There's that corridor down the middle. This is a 40-foot van. You can just barely see the corners of it, but the snow drifts in Savunga pretty well. The configuration of that foundation, the wind actually blows underneath the plant and helps scour the snow. It's Arctic Engineering 101 is to try to get your buildings up so you can get some scour and keep the area clear. We were all very happy that this was working, and then the plant operator sent me this picture. Sometimes the wind rotates around, so you have to kind of position your plant so it sweeps past the door. Sometimes the wind comes around and blows right down the corridor and it fills it up with snow. So it works most of the time. One of the great decisions in any power plant is what kind of engines you're going to put into it. Engines have gone from what we call big dumb iron to these new electronic lighter weight engines. They're great for fuel efficiency. These are a pair of 3456s that are in our new Stebbins power plant. Like the state, we've learned that you can put marine manifolds on these. With the help of Gray Stasel Engineering, we've got the latest and greatest of 2005 engine technology. There's a whole bunch of stuff with EPA that makes it difficult for us to install new engines, but these are the most fuel-efficient engines that we can find in the power range. We've put marine manifolds on them so they can extract more heat. We've taken the fans off the front of the engines. We run the fans for both the cooling system and also the charge air coolers with variable speed drives. You end up getting a lot more electronics to support your diesel engine than you ever had before. We've also got a thermal management panel which helps control what's going on inside the cooling system. Another benefit in the Stebbins plant is, again, they're all identical engines. So we're using our automated switchgear to load share in parallel to meet different loads. But we've got a maintenance requirement where now we can share parts and filters, and it's a lot easier to maintain. This is a graph of the cost of electricity that we've had from 91 up to 2013. And back in 1991, fuel was maybe a third of the cost of power for us. You can see this pink band or purple band has grown and grown and grown, and now fuel cost is more than 50% of the total cost of power in any of our villages. So fuel is king. If you can make a more efficient power plant, that's what you want to do. The corollary to that, because of the cost of fuel these days, is that heat is very important. In a power plant, you're really just trying to get rid of heat, and it actually can cost you money to run fans, to cool your engines, and that sort of stuff. But if you can build out the infrastructure in order to use the heat in other places, then it's a benefit. This is a radiator deck on a new Stebbins power plant. It's got a couple of aftercoolers. It's also got the radiators. These are the variable speed drives that are running those. I guess another innovation that I'd have to tilt my hat to the Energy Authority and Gray Stational Engineering is back on those engines, a lot of times there's a crankcase breather that goes out and gets recirculated into an intake air filter, and those can get clogged and plugged after a while. One of the things that they've come up with is a crankcase breather that comes out and it's actually heated by the final exhaust tube to help atomize any of the fumes that are there and let it go out into fresh air, and that way you're not trying to draw it back through a filter and clogging things up. So it's a pretty neat innovation. So combined cooling systems. Not only is a fan-driven pump or a fan-driven, a belt-driven fan on an engine a parasitic load, all of these engines circulate coolant with a water pump. And we don't add typically booster pumps. We let the water pump push through the cooling system and circulate the coolant as needed. We have found, though, that as you increase the loads or the restriction in that cooling system, the engine has to work harder to circulate that energy. And we can actually calculate fuel efficiencies if you have less head loss through your cooling system. So you want big pipes, you want to have minimal valving, and we used to also put large shell and tube heat exchangers in our cooling systems where the full flow of the coolant would have to go through that heat exchanger. Creates a lot more restriction. Now what we're doing to pull off heat for our power plants is we're putting in what we call a pump node. So you're actually pulling liquid off of one part of the manifold, pumping it through this heat exchanger and putting it back in. That way the engine is just seeing this larger loop, and it's not really seeing the force of having to push fluid also through a heat exchanger. Of course, if you only got one engine running, the other engines are offline. One of the things we do is we put circ pumps off of this coolant loop that comes in and circulates backwards through the engine to keep those engines warm and ready to start at any time. I guess that's it for that one. In this picture, you can see that we've designed a couple extra ports. Basically, this piping is coming around and going out to where the radiators would go. These two ports would be where we would take off and go to another pump node for a larger heat exchanger for a heat recovery system. This is a heat recovery system that was put into Hooper Bay, and it's a little bit different. Again, Hooper's kind of a mixed modular plant. It started out as, back in the 60s, it was a single power plant. As the village grew, we added more modules. So now we've got engines in the original building. We've got 2 additional modules. And ANTHC came in and said, we could use your heat. So they want to put in a heat recovery system. We've got to have individual heat exchangers for each one of those cooling systems that's drawing heat, and it goes into a centralized box. And then they run their water system through that box. And with that plate and frame heat exchanger, we're exchanging temperatures, raising their water temperature and benefiting the city. So on that combined cooling system, this is a closer to finished product. Before you saw a bare pipe, this is with it all insulated. This is where the coolant goes out to the radiators and comes back. And we used to have what you call an AMOT valve in a three-way position, and it's pretty much like a thermostat on your engine. When the engine gets warm, the AMOT valve would open, it would bypass or send coolant out to a radiator, then it would come back. They work, but they're not as precise as you might want if you were looking for a minimum water temperature. So when you put in a heat recovery system, it's nice to have actuated valves that are actually controlled by a PLC or a thermal management panel that can more closely regulate the temperature in the heat loop. One thing we don't want to do is overcool our engines. They become less efficient. So we have to be careful about how much heat we send to the radiators, how much heat we send to heat recovery. With all these electronic variable speed drives, additional things that are maintaining and watching what the engines are doing, you might think that we're increasing all the electrical loads inside the power plants, but over time we've seen that the loads have grown to the point where our station service, basically the amount of electricity that we're using in our plants, continues to decline. And we're still being pretty efficient, even by pulling all those things off the engine. Automated switchgear, again, to be most efficient with your engines and also to help integrate with renewable energy. It's nice to have automated switchgear that will meet the load. There's PLC programs in these units. One of these control panels for each one of the engines, and then there's a master control panel that controls everything, also dispatches individual loads. AVEC has a policy on our distribution system. It's pretty remote villages that we do everything de-energized. So we place a lot of emphasis on sectionalizing our loads out to the village. We've got a lot of breakers inside our plants so that you can turn off different phases, different sections of town to go out and do some work. It's also beneficial that if there's a fault on the line, it'll only trip one section of town. You got time to go and fix that. You don't lose the whole village. The switchgear that we just put in our latest plant in Stebbins is, again, another step up for us. Stebbins gets some of the bells and whistles that a regular plant couldn't get because as we grow, Stebbins is being tied together with St. Michael, so we have a little bit larger plant. It's almost twice the size of a lot of our other plants. We've noticed that when we put in these automated switchgear, a lot of times the size and constraints don't let you get behind the gear if you have to do any changing connections to the buswork, that sort of stuff. So we've gone to what you call a draw-out breaker. This whole panel will pull out. If you have a bad breaker, you can pull that panel out, disengage it, fix it, put it back into place. You don't have to crawl around behind the back of the panels. And the buswork is accessible. This panel actually slides out, and you can actually see the buswork behind there. The next step beyond automation is remote telemetry so that you can communicate and see things from the village. I think there's probably 3 or 4 other conferences that are talking about that, so I'm going to blow through this pretty quick. One of the difficulties is the actual communication link out to the village. We're still struggling with satellite and terra networks and even down to phone modem type of stuff to get reliable communication. A couple pictures. Some of the things you can do with remote communication is operator assistance. You can look at the same screen they're looking at to help them troubleshoot what's going on. Outage forensics. You can get a whole bunch of data that used to come on fax machine. Now it comes right over the line. Fuel systems inside the power plant. This is a day tank, so fuel gets pumped into the day tank for use by the engines. The engines pull fuel out of the day tank. Not all of it gets burned. Some of it goes back into the day tank, gets recirculated. Filtration systems. There's a dual pumping system that the pumps is down here and here, that we use to fill the day tank. If one fails, the other one will work. That way, when you're trying to fill the day tank and it's 40 below in the middle of winter, at least you've got a built-in redundant system. This little valve here is connected to our fire system. If there is a fire in the plant, it will close that valve so that you don't continue to spray fuel into a fire. That's an old standby that's in just about every diesel power plant probably. This has got an oil blender on it, so as you're pumping fuel into the day tank, it'll recirculate, pull oil out of a hopper. Whenever they change oil, they can put it in the hopper, and it'll blend that oil back into the fuel so you can burn it rather than bringing it outside, burning it in a smart ash burner or trying to ship it off site. Again, more electronics, PLCs. This is a day tank control inside the panel, oil blender controls. And in order to prevent any sort of accidental spill, we also have a motor operated or a solenoid valve out in the tank farm so that when the plant operator goes to push the button to fill the day tank, it's opening an electronic valve out in the tank farm that's not open all the time. That way, if there was a break in the line, you don't get spills. Another thing, Brian Gray from Gray Stasel Engineering had encouraged us to try, and so far it's working out well, is a tank level monitoring system. This is a Stebbins power plant tank farm. We've got an intermediate tank, which you take fuel out of the bulk tanks into the intermediate tank, and then that day tank we were just looking at fills from here. From inside the power plant now, the plant operator can see the product level in that day tank. He can see the fuel level in the oil hopper, and he can also see the fuel level in that day tank. This is a NiCad battery system. We usually have power supplies to help bolster any sort of DC power in all our control gear. This NiCad battery system would run all the engine starting ability. We put in a bypass feeder. There's a battery charging system just like you would have in your garage if you wanted to charge your batteries in your car. That keeps those batteries topped up, runs off AC power. But we also have an outlet and a switch so that when we draw the batteries down to a point where you can't start your engines anymore and it's cold and dark and nothing's running, you can always hook up a 5 kW portable generator and recharge the batteries. One of the things we do to support the batteries is put in ultracapacitors. It's a little bit different technology than batteries. Ultracapacitors kind of work on a solid state rather than chemical reaction. And we're using these both in our control panels and in our battery banks. Some of our older plants we've seen where we've got NiCad batteries that have been out there for 20 or 30 years. Now that we've gone to automated starting, we're doing a lot more cranking on our engines. We see some depressed voltages, so we put in larger ultracapacitors to help support that cranking time. They're really good for a big punch right on the start to get engines started. Then the battery can take over and continue the crank. Also, with any sort of cranking, a lot of times you get these little dips, and computers and PLCs and all those electronics we just looked at don't like to have that variation, so the ultracaps are there to kind of pick up the load. In order to make that work with our system, we're modifying our DC breaker panels so that it can feed either off the battery bank or off the ultracaps or off this power supply. And there's diode bridges in there to direct which way the power is going. That's just a schematic of what we were looking at in real life. So most of those innovations that we looked at as far as making the engine more efficient and reducing energy costs and everything have gone up and down, and you can see there's a blue line where without renewable energies it kind of continues off on that flat curve. In about 2005 we started adding renewable energy, and you can see that the system averages get to go up quite a bit when you add obviously something that doesn't burn any fuel and provides power. So in 11 different villages we've now got wind installed, and there's other conferences that are talking about the integration, how to make it work. Our state-of-the-art technology at this point is the integration is really the backbone of it is a secondary load controller, which is an electric boiler which rapidly fires different heating elements of different sizes to help control both voltage and frequency. Again, there's, sorry, we're getting close. There's a wind dispatch panel which looks at the loads of the village, which engines are online, tells how many wind turbines can run. There's the dispatch control also tells the boiler which elements to fire, all those sorts of things. It's more and more getting to be a computer technology world, whereas, you know, as other speakers have said, back in 2000, you know, 14 years ago, it was fuel, air, diesel, make it run, and that's about all you needed to know. Wind production, very variable. One of the things that we're looking at in order to determine how much load we can put on our PLC or our SLC is what we call an instability factor. And unfortunately, right when the wind is ramping up, there's a very steep curve, and a little bit of wind variation creates a big variation in power. So not only do you have to use that SLC to maybe take the top off of too much wind production, but you have to use it to create stability in the middle of that production. So you might say, well, it's terrible. You're heating water when you don't even have enough wind to fully supply all the power that you need in your village, but you really need it there to help create stability and keep the lights on. So this is Stebbins plant again. This just came on in the spring, and we're still working. ANTHC has a project going forward now. They're putting in heat recovery to the rest of the village. Well, there's, I think, 5 different off-takers, both community buildings and the school. We've got grant applications in for wind generation. We're going to be building a tie line to St. Michael this winter, and hopefully turning off the St. Michael power plant and just going to standby generation on that side. And then we got to work out the telemetry with the standby generation tie line. So there's still work to do. Any questions?
Yeah, out of the 58 villages, how many of them are you doing heat recovery with?
I'd say about a dozen. I don't know the number exactly, but a lot of the ones that are in place were actually built by the state in the 80s and have been maintained over a long time. Some of those have fallen out of use. There's been a resurgence since 2008 when fuel prices went through the roof. Everybody realizes, hey, heat's a big commodity, and there's been a lot more interest in it as of late.
Your side or?
Well, on our side as well, but we're not quite ready to get into the district heating business. We're a power company. We really don't have the expertise in that, and I guess we haven't made that step. Bethel, again, is changing our paradigm. That power plant comes with a district heating loop that they maintain. We're learning and we're growing. So, anybody else?
Thank you for sharing. So our next presenter is Dave Pelunis-Messier. Oh, I butchered it. Everyone knows him as Dave PM. He studied at Cornell University. He's been a wild energy enthusiast in rural Alaska for the last 5 years. He is the Rural Energy Coordinator for Tanana Chiefs Conference, the tribal nonprofit for the interior. His past projects have included small wind, solar PV, solar thermal, hydrokinetics, regional energy planning, and energy efficiency. He is currently assisting the tribe with the installation of a 17 kW solar PV project in Fort Yukon, assisting McGrath with the VEEP project, and working with Koyukuk on power plant upgrade. The title of his presentation today is Improving Supply-Side Efficiency, and he'll provide tips for better monitoring your powerhouse for fuel savings, which I think means more money in the bank. So please help me in welcoming Dave.
Awesome. So I was just joking with Monty. I feel like I'm in the middle of a smart guy sandwich. So my presentation is definitely not super technical. I end up working a lot with rural communities, and so it's kind of to some extent geared to that level. And TCC is also not a utility, so we do not have the experience of the folks at AVEC. We kind of have the experience of communities coming to us and saying, hey, we need help. and trying to address those needs and working with project partners at AEA and other entities, Denali Commission, to try to come up with ways to help those communities. So I realized during my last presentation I didn't really explain my region. So for folks who are not familiar with the Tanana Chiefs Conference region, this is a map of the Tanana Chiefs Conference of the interior of Alaska. I believe we're about the size of Texas. The majority of our communities are obviously off the road system. We have a few communities that are on the road system down in the upper Tanana region, and then Tanana, and then some that are further out, kind of Manly Hot Springs and Minto, and then Circle is also on the road system, and Eagle, lest I forget Eagle. Everything else is fly in or boat in only. So as a consequence, when the villages were electrified, they chose the most, or one of the most energy dense resources in the world, diesel. Diesel is what was going to power them. And that worked great back in the 70s and 80s, and it's continuing to work really well. The problem is the cost of diesel has gone up because it's such an exportable commodity. So I don't have to tell everybody in this room, you all know that the cost of power is increasing significantly. These are some highs. Takatna is $1.02 a kilowatt hour, which, to put that into perspective, I think that's about 10 times the rate for Anchorage large commercial. Arctic Village is right around $10 a gallon. So costs are very high. It's becoming very difficult to live and work in rural communities, and also to fund school systems, to fund post offices, et cetera. So as folks, again, kind of keep mentioning, there's a lot of components to your electric rate. The biggest one is obviously the cost of fuel. But one of the things that I've been realizing is it's not just the cost of fuel that separates a high efficiency or a community that's got better efficiency from a community that's got lower efficiency. There's a lot of other factors in there, and for one reason or another, I think that those don't get brought up enough. But they are one of the that's an important factor in figuring out how can we reduce the cost per kilowatt hour. Let's look at these other factors and analyze them and figure out what it is. So again, most people probably know two big components of your electric bill is a utility charge, and that's made up of a variety of factors. This is GVA, My Electric Utility, here in Fairbanks. This is what the utility charge covers. And then there's another section, which is the fuel and purchase power. And so when you all get your electric bill, those are probably the two largest components of the bill. And here in Fairbanks, you'll notice that it's about even, right? Fuel and purchase power, about half of the cost. Cost per kilowatt hour in Fairbanks is roughly 20 cents. So this is direct from my bill. About 10 cents per kilowatt hour is a utility charge, and about 10 cents per kilowatt hour is the fuel and purchase power. So let's bring that example out to rural Alaska and see the difference there. Non-fuel costs make up about 18 cents per kilowatt hour, and then the fuel costs are right around 46 cents a kilowatt hour. And one thing I like to stress to communities is that a lot of this information is available right on the Power Cost Equalization Forum. I know that that information is not always perfect, and as Jeff Williams likes to remind me at AEA, it's only the PCE data is only good as the person writing it down on the other end of the phone. So take that with a grain of salt, but I call this a good start and a really useful piece of information. So when we're looking at what makes up the cost per kilowatt hour of a gallon of electricity out in the communities, it's important to kind of have these reference points, and also look at this efficiency of the genset, which folks have been stressing. A lot of my communities are standalone utilities, standalone electric utilities, so they don't have the power of AVEC or the power of TDX behind them. They have the power of let's say almost 200 people out in Ruby, Alaska. That's the kind of the talent pool, if you will. They don't have an engineering staff in Anchorage and Ivy League educated engineers. They've got the people who are available in the community and the people who know how to keep power plants running, but maybe not, maybe they don't have all the expertise to run those as efficiently as they could be running. So this is an idea that I'm sure has been talked about a little bit. Everybody knows what their miles per gallon on their car gets, right? Pretty much. Folks know if they've got a Prius or if they've got a truck, it's going to be a lot different. So something I'd introduce is kind of this idea of kilowatt hours per gallon. And it's something that's readily available, and if we want to lower the cost per kilowatt hour, really obviously need to look at how we can improve that kilowatt hour per gallon. Again, kind of looking at the numbers from the Power Cost Equalization reports. I've got two columns here. These are some of our communities that are not getting that are not as efficient. These are some of our more efficient communities. Anybody want to take a guess at what the difference between these two columns is? Say that again? That's a common thought. Anyone else? Come on, guys. Road access. Give me someone else. All right. ANVIC. Bill, is ANVIC a AVAC community? Yes. Yes. How about Holy Cross? Yes. How about Manly? John, that's a TDX community. So you've got cooperative, private business. So those three communities, right, are all communities that are supported they have an engineering staff in Anchorage, as I just said. Those are all communities that, as you can see, and I just took three that Beaver, Alaska, Beaver Joint Utilities, which is owned and run by the tribe, manages the Beaver power plant. In Igiugig, it's a city-owned power plant, so they manage it. Venetai, it's owned by the Venetai tribal government. So again, I just kind of brought this comparison. You know, obviously there's a lot of different factors that go into the load profile of a community. And a lot of different factors that go into the efficiency of a generator. But something that I don't think maybe gets talked about enough is kind of the support for the rural community or the rural utility that's out there trying to keep their power plant running. And one of the things that we've been looking at TCC is how we can provide better support for Beaver, for Igiugig, for Venetai, for Takatna at $1.02 a gallon. For some of these rural communities that don't have the resources that other communities do, to essentially do that, to bring up their kilowatt hour per gallon efficiency, right? Because that's going to hopefully lead them to lower lower electricity costs. So how do you improve your kilowatt hours per gallon? And this is something I always stress. Know what it is to begin with. A lot of rural communities, at least that kind of come to TCC and say our energy costs are really high. Maybe their accounting or bookkeeping isn't necessarily in order, and they're not sure what they pay on a year-to-year basis for fuel. So I know a lot of emphasis has been paid towards fuel, bulk fuel purchases. That's one way, but you've got to know, you've got to have your books in order, obviously, in order to know the difference from one year to the next and know the difference when one generator goes offline. Hey, let's just switch to another. Maybe that's not the most efficient, and I'll go over an example of that in the future. So there's obviously also a lot of different other methods to increase your fuel economy, to reduce your energy costs. There's switch gears that are coming online that, better monitoring. AA has been great at with their SCADA systems. Electronic governors provide a lot better kind of response time, if you will. Running different generators at different times. One of the biggest things that we've identified is getting generator operators down to the free trainings down in Seward. And I think that, I've spent a lot of time in the communities. I think one of the things that folks maybe don't realize is that they get approached a lot with these free trainings, but I think the connection doesn't always get made between attending these trainings and having your power plant operator trained up through all of the different tiers of the power plant training down at AvTech and lower energy costs. But I believe there's a significant difference, as you saw the difference between having that, that support network of engineers versus not having that support network of engineers. That's a very significant difference in the efficiency of your generator system. And then also, obviously, complete your efficiency measures, so right-size your generators. Or I'm sorry, after you complete efficiency measures, I should say, right-size your generators. So in other words, one of the, I guess, reasons I've heard tossed out there for against efficiency is, well, if we do too much efficiency, the generators won't be the right size for the village. To me, that's kind of like, well, I've got a family of 5, so I got a minivan. And then all the kids move out of the house, and I want to get better fuel economy in my minivan. Better get some more kids, right? Come on, get a better vehicle. All right, so with this in mind, we did a fuel monitoring project. We had some energy efficiency conservation block grant funding in Beaver. And in Beaver, they're one of the communities that we work with that, that is struggling, let's say, that doesn't have that backdrop of engineers down in Anchorage. They've got Beaver Joint Utilities owned by the tribe. So they've got 3 fairly new gen sets that the state of Alaska, AEA, put in. I believe it was completed in 2008. They've got one 110 kW John Deere and then 2 67 kW John Deeres. And their average load is right around 30 to 50 kW. So we had some funding, and we have been able to purchase and work with a distributor down in out of Seattle that has these very high accuracy flow meters called CRAL flow meters, and they're used a lot in the shipping industry, right? If you think about it, shipping and rural islanded grids, not super similar. They both have onboard generators. They both go through a lot of diesel. So borrowing from an industry that is really concerned about fuel flow and using it in rural Alaska maybe makes sense. So this is a printout, and basically what the CRAL flow meters give us, and over a period of time, and I want to say they're 10-second intervals throughout the day. They may be even more defined. They might be down to 1 second. I'm not 100% sure. I was really hoping to have more time to kind of process the data that we've been getting before this presentation, but time is something they don't have a lot of right now. But basically, we get updates on a daily basis that compares the draw in the community, the load in the community, to the average fuel flow. And the CRAL flow meters are said to be about 0.1%, or accurate to 0.01%, I believe. They have a measurement on the supply and the return side of the fuel flow, and they also correct for temperature. So we went out and installed these flow meters, and then AEA actually sent one of their circuit writers out, Shannon, and he helped us connect into the switchgear. So we're comparing the fuel flow to the load in the community and getting data sent out to us. All right, and so in my position, I get to go out and like I said before, I'm not an engineer, but some things are just kind of obvious. And when you go out to a community and they've got one working generator, the other one's down for parts going into winter, you say to the community, it's a really good idea to change or to get somebody out there to fix that generator, right? But I don't have any more specifics than that. I can just say, you guys should really get somebody out here to fix that smaller generator because your larger generator is not running as efficiently. But I can't quantify that, and quantification of that number is really important. So once we installed, so that's what happened. I went out to Beaver, I believe it was last December, and their smaller generator was down. Simple fix, but their generator operator kind of didn't feel comfortable with the repair, let's say. And so they were running their larger generator, went into winter with one generator. Not the smartest move, but that was the choice they made. And I said to them, I said, you guys should really send somebody out here to try to fix that smaller generator so you can be operating more efficiently. Well, we were able to quantify that after we installed the fuel monitoring system. So now I can go out and I can say, you know, that 110 kW John Deere is using 2.82 gallons per hour. That 67 kW is using 2.52 gallons per hour. Geez, my apologies. And that seems good enough, right? It's only 0.3 gallons. Well, if you multiply that out over the entire year, it's fairly simple to see you're consuming about 2,600 gallons more than you have to. And in Beaver, they pay roughly $6 per gallon delivered out there. I believe it's got to be flown in. Most of the time, it's got to be flown in on Everett's. So all of a sudden, spending $2,000 to $3,000, even if you have to go out and get Craig Taylor, which the tribe did, to come out and repair your diesel genset, that $2,000 to $3,000 bill doesn't seem as expensive once you realize that 0.3 gallons per hour is costing you $15,000 a year, almost $16,000 a year in fuel that you don't need to be going through. So let's get somebody to fix the generator. And then I brought that example out to these other communities that I work with, these kind of, let's say, less efficient communities. Beaver, Koyukuk, Venati, let's just say they were getting the same efficiency as those other communities. The communities that are roughly the same size, have a school, have a water plant, roughly the same infrastructure, but have the support staff to get more efficient kilowatt hour per gallon. So, I mean, this is the difference. If Venati was getting the efficiency of Holy Cross, they'd be buying 7,400 gallons less each year, right? Fairly simple math, but fairly astounding numbers. So if I was to do this for all of the communities in my region that aren't getting, you know, very phenomenal kilowatt hour per gallon efficiency, at the end of the day, if I totaled all those up, it would be a fairly substantial number. So trying to get these kind of, not sure what to call them, more independent, the communities that don't have the support network up to where these communities are is a big priority for TCC and a big priority for keeping these communities functioning and healthy. So steps forward, again, we're a native nonprofit. We don't have the, some of the firepower, the engineering firepower, let's say, of a utility. But we were able to pass a resolution for all the good that those are, and we are encouraging folks to attend the Alaska Energy Authority trainings down in Seward, the free trainings, stressing that. And then we set a goal of being able to get, or trying to get, all of our rural grids in our region to produce at least 13 kilowatt hours per gallon. And numbers like that I think are really important because they allow you to measure yourself. If you don't, let's say you don't make 13 kilowatt hours per gallon, let's say you make 12, but if you started at 10 kilowatt hours per gallon, you're doing pretty good. So it gives us that method of benchmarking. And hopefully at the end of the day, through partnerships with the Department of Energy, with the Alaska Energy Authority, and with better training for our communities, we can get more of our communities up to that 13 kilowatt hour per gallon goal, and hopefully even further. Another note similar to the kilowatt hours per gallon that we realize is that some of these communities, again, that don't have the support network, they're having the same problem with their waste heat systems as they are with their generating systems. And part of that is just an inability to see it. We're going through this with the community of Koikuk right now in the school district. There's really no good benchmarks and there's no good monitoring, BTU monitors that are accurate to determine, you know, is the school receiving as much benefit as the powerhouse is pulling out, or as much heat as they're putting out towards the school? We're not sure, and if you don't have the monitoring in place, you can't really be sure. But once you get the monitoring in place, once you start to get that baseline data, you can realize problems and make corrections. And then also, sometimes you just need to spend the money to save the money. The community of Beaver is a great example. If they had spent that money a little earlier, they would have seen a significant savings and not spent as much on fuel. So that's about it for my presentation. Thanks, guys.
Sounded pretty straightforward. Did anybody have questions for Dave? You fascinated everybody. Thank you. Well, this next presenter, I would like to welcome as the resident of Igiugig by now. He spent so much time out there this summer, we're going to claim him. Monty Worthington has been working in the renewable energy field for 15 years. The work has included solar, wind, micro hydro, and hydrokinetic energy projects ranging from grid-tied commercial projects to isolated microgrid and off-grid renewable energy system installations, and I think he prefers rural areas such as rural Alaska, the Pacific Northwest, and rural Asia. He currently works as Ocean Renewable Power Company's Alaska's Director of Project Development, overseeing the development of their RivGen power system, remote community in-river hydrokinetic projects, and tidal energy projects in Alaska. He's a very busy guy. His presentation is titled RivGen Power System Commercialization Project. And in the beginning, I didn't introduce a lot about Igiugig because I figure he's going to speak on behalf of his home community. But I wanted to congratulate him beforehand that most people know Igiugig for the fishing and the largest salmon run left in the world. But this year, I think ORPC brought out as many tourists for their RivGen device as we had fishermen. So thank you.
Thanks for that introduction, AlexAnna, and nice to know I'm invited to be a member of the community. So just wanted to, as a bit of introduction, I work for Ocean Renewable Power Company. The company is based in Maine. We're a private company, and we develop hydrokinetic technology and also hydrokinetic and ocean energy projects to bring those renewable energy resources to the major grid down in the United States and elsewhere, as well as in Alaska here. And I have been working for the company for about 5 years. I wanted to give a special mention as I started here to we have a lot of partners on this project, the community of Igiugig being one of the big ones, but also just to the Alaska Energy Authority and the Denali Commission, who really provided the opportunity and the funding to get this project off the ground through the Emerging Energy Technology Grant and Emerging Energy Technology Fund programs. And it's been a really, to me, a very big success this year for those programs. We've seen 3 hydrokinetic projects get in the water in Alaska and produce power, all funded through that Emerging Energy Technology Program, which I think is a huge success. And I salute the vision of everyone who's worked on and around those efforts. So to start out with a little bit of a history of this project, there's several people in the room who were involved when we first kind of conceived of this. David Lockard there and near the front, one of them, and I see Brian Hirsch in the back. But we began talking about this project back in 2008 in the AEA office. As we had started, Brian and I were working at the Watershed Council, and we had started working with hydrokinetic technology and heard about this other company, Ocean Renewable Power Company, who was interested in. And David brought us together there, and we started brainstorming about doing a river project. And it all sort of began there, and we quickly moved up to Tanana as a test site, and the university and ASEP became involved. And we've now seen that test site be developed by the university into a world-class test site that had the AlexAnna device being tested there, and I know some people got to go see that Monday, and that's also just awesome to see these things moving along. Along the way, we were able to secure some funding initially through the Emerging Energy Technology Grant to build and test some components of this system, and then through round one of the Emerging Energy Technology Fund that actually paid for this demonstration project to bring this hydrokinetic power to the village of Igiugig and harness the Igiugig River there. So as I was flying up here this morning and working on this presentation on the airplane, as I normally do, I started thinking about, well, what were the challenges we had to overcome to get to this point and get this system up and running? And I started thinking about, and why. And really, the big question that's been on everyone's plate since we had that meeting I spoke of in 2008 is, can hydrokinetics be a meaningful part of the energy portfolio of rural Alaska? We have lots of moving water, lots of rivers, lots of tides, but is it really something we can use? And that's really the goal of this Emerging Energy Technology Program, is to see, can these technologies really work? Are they a viable alternative? So you start with that question, and then you start looking at, well, what are the other questions? Are there a significant amount of viable resources? And we've started to do some work to answer that. And how do you reliably operate technology in these environments, adapt it to these environments? And then you start thinking about that, and you end up with this litany of questions. And I kind of started writing these down and thought of all these things that we worried about at the beginning of this field season. Is this going to work? Is that going to work? And I thought about all the conversations I've had over the years where I've been cornered and been told all the reasons why hydrokinetics probably isn't going to work. And I kind of got a little bit paralyzed at this point in writing my presentation. I thought, how am I going to explain this? And it made me think of a story from a few years ago. I was working on a tidal project in Cook Inlet. We were collecting data, and I was out off the East Foreland in October, and it was kind of a crummy day, and the tides were flowing like they do there, and there was this huge washing machine of a whirlpool behind us, and we were working to pull up this hydrophone we'd had down there, and it's about a 700 or 800 pound mooring, and we were in a pretty small boat, feeling pretty little out there, and I was working with this crewman who I'd never worked with before, and he was a really adept guy in the boat, just really working well with me, and he was a lifetime commercial fisherman, and I lived in Anchorage, and I was kind of looking around, and we started pulling this mooring up, and we got it just a little bit off the bottom and ground the winches to a halt, and we're kind of stuck and couldn't seem to get it to budge any further. And this guy, and I kind of looked over at this guy, and I thought, gosh, I get myself in some really crummy situations doing this work sometimes. And the weather's kind of picking up, and I looked over at him, I thought, gosh, how did I get this guy involved in this? He probably got a family back in Anchorage, and what's he thinking about this? And he looked up at me and he said, so how much is this hydrophone worth? And I thought, well, it's probably about worth as much as your pickup truck. And he's kind of looked and he thought a little bit, and then he looked back and he said, well, how do you eat an elephant? And I'm in the midst of trying to pull this thing off the bottom. I'm like, I don't know, I've never been to Africa. I mean, is that legal? Is that sustainable to eat elephant? I don't even know. And he kind of looked back, and we can tell I was really confused. And he says, one bite at a time. And he reached into this bin and pulled out a chain and another pulley. And we managed to pull 5 feet of this cable up of 200 feet and reset it and pull another 5 feet up. And an hour later, we had this hydrophone in the boat. And he taught me a lesson that day, just about staying focused, not on the big picture and the waves and the wind and the tides, but what you're doing in the moment. I think not only in hydrokinetics, but in all the work we're doing here in Alaska and rural energy, it's a huge problem. It's an elephant. And how do we tackle it one piece at a time? And that's essentially how we tackled this project. So the big question is, how do you eat an elephant when you have all these issues to deal with? And we approach this through starting with each component, all these different pieces and parts you have to answer all those questions I had up there before, and verifying they work on their own, and then working to integrate them into a system. And this is some pictures of different stages along this journey. The anchor there is being deployed at Tanana back in 2011 and tested to see if it held and worked right. Our pontoon support structure being tested in Igiugig. That's the turbine on the east coast in the bottom right there, and our SCADA system. But you have all these different components to work at and sort of reduce the risk and all the different things that could go wrong with each of these things along the way. Let's see. Am I pushing the right button? Oh, there it is. And so we also developed and started working at a lot of different sites along this journey. We, as I mentioned, we started working at Tanana on the Tanana River and did our first anchor testing there, did our first work trying to characterize the resource, starting to do some environmental work. When we got to looking further at that site, we realized we needed to reduce our risk where we're going to be working a bit further. So we started working in Igiugig, what we called our virtual river test site, where we could pick the currents we wanted to operate in. We weren't stuck with one solid flow that we couldn't turn off. We could say, okay, we're going to test in this strong of a current today at this time, and we're going to wait for slack tide if something goes wrong. And so we started working there in Igiugig. And then at the same time, on the other side of the continent, we were working in Maine to test the turbine generator unit and make sure that that would function on its own and produce power from moving currents. And we did that in Eastport in the sort of the bottom of the Bay of Fundy there. And then along the way, we got introduced to the village of Igiugig and realized that was really an ideal first site to begin working on. It's an absolutely beautiful river. If you've never been to Igiugig, it's crystal clear, full of fish, and very little debris, which is nice from a hydrokinetic perspective, and not a lot of silt, so you can really see things. So we realized that was really an ideal site, and the village had already been working through a REF grant to develop that site. So they collect a lot of great data, and we started working with Igiugig. I think it was back in 2012 or 2011. I'm not sure now, but it's been a while. So fast forward into this year, through the original grant, we developed these components. We started working on getting them to the point they could be integrated and actually doing a demonstration of this power system at Igiugig. That all started this spring at Igiugig, and that began with testing, deploying, and retrieving this full device, which is a pontoon structure that has the turbine on it. And we realized this was sort of a risky aspect of our deployment to sink this thing to the bottom and recover it while currents were flowing. So we decided to build what we called a surrogate TGU. This is sort of a dummy weight that has roughly the same center of buoyancy and center of drag as the turbine. And that's that object in the upper right. It's made out of railroad wheels and salvage steel. And we attached that to the pontoon support structure. And at the Igiugig site, we started working in still water and gradually increased till we were working in about a 4-knot current, 2 meters a second, of sinking and retrieving this thing. And that worked actually really well. We had some challenges along the way, but got that up and running, had some folks down to see that operating. There's a picture of it being retrieved there as it's coming up. It actually comes up sideways, and we sink it sideways. And then we also tested towing it, moving this device along, see how fast we can push it with boats, and got to where we could push it at the speeds of the currents there. So kind of did everything we could at that site to show that we could deploy, retrieve, and sort of operate this device without actually having the turbine, which is still being shipped from the East Coast. The next thing was moving this whole turbine to Igiugig, which is one of the great aspects of this project. Is this is a turbine that's designed for rural Alaska. Well, it has to get there first to be used there, and this stuff gets heavy when you're dealing with the kind of loads you have to work with in the marine environment and the river environment. So shipping it's not trivial. And here are some pictures of the journey it took from Igiugig down the highway to Homer, then across Cook Inlet by boat, then up the Powell Bay Road to Lake Iliamna, then back onto a boat and across Lake Iliamna. There it is being pushed across Lake Iliamna, and then to Igiugig. And there's also, I did my best to try to put a video in this, but I don't think it worked. But this is a picture of how we actually roll the device up and down the beach on some rollers. Because once this is assembled, it's about a 50,000-pound piece of equipment, and how do you move that in a village? So we developed a system with some air rollers under it to roll it up and down the beach. So this is June in Igiugig. All the components arrived there, and we worked on putting this device together with some spectators who would take time out of their afternoon swimming breaks to wonder what we were doing there on the beach, getting in the way of things. But it was a fairly straightforward assembly. One of the great things about working in Igiugig is it is a village that has great sort of resources in terms of equipment, but even more so in the guys that operate it. They've got a very talented, very capable crew there. So we had awesome support from the village as we worked on putting this all together. So then we began working on what we hadn't been able to do yet, which was test all this in a river, which is a bit different than doing it in the tide or in the lake. But we decided, hey, let's start in the lake. So we worked on deploying our anchors, which is something we hadn't done yet in any except in the Tanana River, and testing how we would deploy and retrieve these anchors. And also got experience working how we ended up working the river, which was using a flexi float barge they had and putting these excavators on board to sort of operate as cranes. And we would use these to move all the heavy equipment in and out of the water. And those anchors were one of the more challenging things. They weigh about 13,000 pounds apiece, and putting them in the river when the current was flowing at about 5 knots was pretty tricky. But again, it was a lot of planning and also local ingenuity and skill that really enabled us to do that. And this is some pictures of his first testing deployment there in the lake before we put him in the river. And then we got to working to get the device down to where the anchors were. And we tried towing this device again to see if we could push it at 5 knots that we need to do to navigate safely in the Igiugig River there. And we realized we couldn't push it that fast. We could really just push it at the 4 knots we realized we could at Nikiski. So we actually left town and went back to the drawing board and said, well, we'll come back and we figure out how to get this thing to its mooring system. And we came up with the idea of loading the whole thing onto this barge, because the barge will push a lot better than the device itself in the water. And so we came back a couple of weeks later and practiced putting the RivGen up on the barge and then pushing it around, and we could easily push it up to about 6 knots in this configuration. So we realized that would work, and after a few more fits and starts, we got the RivGen onto its mooring system and deployed in the river in the Igiugig there. And we actually launched it off that flexi float. We hooked it to the mooring system and then essentially pulled the flexi float out from underneath it using the excavators to help the bow, sort of ballast the bow down and get it to sweep out from under the RivGen. I have a video of that, but I'm obviously no good at putting videos in PowerPoint, so you won't get to see it. But it worked well. We got the RivGen on the mooring system, and then we began the work of deploying the data and power cables to shore. LGL was there to do some fish monitoring. They hooked up cameras. They had cameras and lights hooked up so they could do monitoring of the fish interactions. And then we went about syncing the device. And this is some pictures of the device going down for its first time there to the bottom of the Igiugig River. And it's always one of those moments where you wonder if you're ever going to see this thing again on dry land, because it's really out of touch once it's down there. It's about 20 feet deep there, and the current's moving about 5 knots. There's really no way to do anything to it until you get it back to the surface. But the deployment went very well. All the cables remained intact, which was really important, so we could monitor it, both the fish monitoring and get power from it. So once we got it up and monitoring, this is a picture of it at night with the lights from the fish study cameras on it. And we had LGL, as I mentioned there. They were doing studies. Every time we operated the turbine, they had cameras running to see what kind of interactions any of the local fish species would have with the turbine. And then we also had the University of Washington researchers came up under some funding that our company secured collaboratively with them. Through the Department of Energy. And this was to study the inflow to the device, the wake of the device, the turbulence around it, the acoustics of it. So they were there for about 10 days, also became regular members of the community, I think, in that time. And did a bunch of great work on the river, in and around the device, and really helped us characterize its power output and also help us understand ways to improve it in the future. So 2 weeks ago, after that device was in the water for a month, we went back to Igiugig and for the final step of this season's field work, and were able to successfully retrieve the device after it had been down there. We'd pulled it up once mid-operation to do a maintenance event, but it had been down for a few weeks, and we pulled it back up, and very successful with that. We were able to disconnect it from its mooring system and put it back on the beach. We then disassembled the device, and the turbine is currently on its way back to the mainland. We're going to do some more work on it this winter before shipping it back to Igiugig next summer for more work there in the village of demonstrating the project and continue to work to refine this. And in the context of sort of the modernization of the Powerhouse, this is sort of just a supply side alternative that we're working on to develop to both reduce fuel usage and hopefully create some alternatives to diesel as a primary energy source in some Alaskan communities. I wanted to kind of point out, I mentioned it a few times, but it's really the people in the field that made this project happen. And I think without any one of the people up there on the screen, we would not have been a success like we were. It takes everybody. There's a lot of people who aren't up there too. And AlexAnna knows there's lots of people in town rooting for us and working with us and encouraging us. And this crew all made it possible. And it really, hats off to everyone. It took a lot of ingenuity and a lot of courage to make all these different steps come together. So sort of the next question is, where do we go from here? As I started this talk by mentioning that we'd had 3 successful hydrokinetic projects in the water in Alaska this summer. And how you gauge success is varying degrees, but these all produced power from river currents and all successfully got in and out of the water. And these are all big challenges. And I think we're at a point in this sort of technology development where we're beginning to retire some of the risks associated with technology. And we're beginning to see that all those reasons that it's not going to work, we're picking them away, and we're saying, no, we can solve this problem, we can solve that problem. So if we can get this technology working, where do we go from here? And this slide here is one that I borrowed from Levi Kilcher at NREL. He made it for a presentation he did last year, I think, but it sort of overlays Alaska's rural communities, the cost of power there, and their size, and the resources in Alaska. And one of the striking things on that is you can see that they're all either on the coast or they're on a river, a lot of them on a river. And we really do have a lot of these loads close to these hydrokinetic resources. So I think Alaska has a lot of potential to be an early adopter because of the high cost of power we have in these remote communities and because of their access to moving water. Most Alaskans depend on these rivers. Most of these villages were situated there for traditional reasons of food gathering with salmon, or on the coast for the same reasons, but now they're close to these energy resources. So I think Alaska is positioned well to be sort of a niche market as these technologies are rolling out, and because of the Emerging Energy Technology Fund, the industry's working here. And without it, it really wouldn't be. These projects would have happened other places, but that fund really brought that work up here. So as we go forward in our particular project on the RivGen, this sort of outlines how we see the future rolling out. As I mentioned, we were able to leverage some of the federal funding sources that we have tapped into. The USDA, through a small business innovation and research grant to develop our first commercial product, is going to help pay for improvements to the RivGen and its redeployment in Igiugig next summer. Also that DOE funding, we call it our DOE Controls Project, to enhance sort of the power extraction of the RivGen, is going to be utilized to support that work in Igiugig next summer like it was this summer. And so we're going to be working there again next summer, doing more technology development, further refining this project and making it commercial ready. And then also using that information and our funding sources to design the first commercial RivGen. Yesterday, the Village of Igiugig and ORPC worked with them to submit a grant application to the Renewable Energy Fund, and that is to do a commercial hydrokinetic project in Igiugig in 2016, leveraging all this work we've done to date and next summer's work as well. So if all goes well in 2016, we will also be in Igiugig, and we'll be installing Alaska's first commercial hydrokinetic project on one of the most beautiful rivers on the planet. And it's thanks to all the people who were working on it with us. So that's all I have.
Thank you, Monty. Are there any questions? Well, I'm going to close this. Oh, sorry.
Hi, my question is for Bill with AVAC. I'm from the village of Nanapichuk, and we share the electricity with our neighboring village, Kasigluk. And our biggest problem is the aging of the poles. in the near future, do you have a plan to come in and replace those? Because currently we're having more outages than we'd like. And when they do come back on, they're not coming back on at the same time. Like, for instance, Kasiglok, when half the village will come on. And in our village, only part of it comes on. And we're thinking it's all because of the poles.
We do definitely have a aging pole problem throughout Alaska. A lot of the infrastructure that was put in the 70s. Typical lifespan, they say, are 30 to 50 years for poles. So we're getting to the point where we need to go out and do wholesale replacements. There are projects underway that we're buying additional poles for every village. New Napachuk obviously has some of the more difficult soil conditions to deal with in order to move poles to site, get them put in, digging in permafrost or thawed permafrost in the summertime, that sort of stuff. But yeah, it's on our list of things to get done.
Yeah, Monty, this question's for you about the Igiugig project. Really excited that you guys have made the progress that you have, and I'm a little bit involved with the wave energy project in Yakutat. So I was hoping you could tell the audience a little bit about the pre-deployment costs that were associated with your project in terms of data collection and how you guys went about that, what the agencies required of you, and how that affected the overall project to this point. Thanks.
Yeah, that's a really good question, Ian. And you know, actually, AlexAnna can speak a bit to this probably, but the original project being developed at Igiugig was through a Renewable Energy Fund grant to the Igiugig Village Council. And that paid for a lot of the background sort of environmental work that you're talking about, like with the Yakutat project, and sort of paved the way for this site to be ready for an emerging energy technology to be deployed there. And it handled all the permitting. It paid for this fish study that we'd be required to do, all these ancillary things. While we were focused on just developing our mousetrap, the village had sort of paved the way that here's a site and it's ready to be put in. So I think it is something, as you look at these emerging energy technologies and getting them in the water, and wave energy is a great example that's, you know, probably realistically where we were with hydrokinetics 5 years ago. We don't have a wave project in Alaska yet, but there's a lot of will to do it. We think there's a lot of resource here. But how do you develop a site so that you can be ready to put the technology there? And this is where the sort of dance between the Renewable Energy Fund and the Emerging Energy Technology Fund is sort of taking place. And I think it needs to continue to be a conversation about that, because if we don't allow feasibility studies through Renewable Energy Fund to support this, then where do we support them? Well, we recognize that it might not, the technology might not be ready for the Renewable Energy Fund, but the Emerging Energy Technology Fund isn't here to support project development. How do we help develop a test site for a wave energy project? So I think it is a bit of a, I mean, I think you've identified a little bit of a funding gap that I know I've had conversations with a lot of people about that, and how do we sort of fill that and develop the first wave energy test site? And I think it is a real challenge, and something that you know, we hope to continue to work on that project. You know, ORPC also participated on the behalf of Resolute Marine Energy, helping with that project a bit, and I hope to continue to. But there is some work that needs to be done to sort of, you know, do all this permitting laundry list and get it ready for all the agencies to say, yes, you can put your wave test device there. So I don't have the answer to it, but I think it's something that, you know, everyone needs to think about as we work on developing that.
Well, what was your expected power outage from the RivGen prototype?
So the RivGen, it's rated at 25 kilowatts, and this summer we were getting between 13 and 15 kilowatts, depending on the stage of the river when we had it deployed. And that was about where we expected to be. We expected those currents to be between 15 and 20 kilowatts. We learned a lot from the university's research there, and we ended up, because of difficulty in placing the anchors, not getting them ideally located. And we had a big difference between the current on one side of the machine versus the other, and that definitely adversely affected our efficiency. So hopefully next summer, we actually moved one of the anchors this fall when we took it out, so we'll hopefully be placed better. We're also doing enhancements to increase its output, but it was within our sort of expectation range, and I think proves that we're not far off the mark of what we expected.
Thanks again, Monty. I'm going to wrap this up. I don't know if you ever knew, but when they actually had to pack up and go back to the drawing board and think about deploying this device, the newspaper called me and said, "I heard the device is too big for the river." So there were a lot of wild rumors flying. What is Igiugig doing now? As you could see with the little kids watching, they had all of the village a nervous wreck for a lot of the summer watching the whole deployment. But the story you told about how to eat an elephant really put me in a reflective spirit. As a tribal administrator, there's a lot of days where somebody will just walk into the office and say, "Hey, we really need a cultural center." So I said, well, if we build one right now, what are we going to put in it? We've got to start working, collecting things, or you have to start somewhere. You can't just go to the end product. Or, hey, we want to start a flying service. And 10 years ago, it was, we really want to get power from the river. So that was the demand of the day, and it took a lot of small steps to get there. Firstly, with renovating our powerhouse, it really needed an upgrade, which is why I really enjoyed this whole panel, because it followed the steps that my village had to take in order to get to the RivGen. So first, the powerhouse upgrade. We're still understanding how to get the most kilowatt hours per gallon. I'm not a mathematician either, so I really enjoyed Dave's presentation. And then what do we need to become a test site to use to test hydrokinetic power? Will it even work? So I think it was just a fitting set of presenters, and I'd like you all to show them our appreciation.